Okay, the timer started. Okay, let's get started. For those of you who don't know me, my name is Kush, and I was a Facebook staff machine learning engineer for most of last 2 years, and ML staff engineer or tech lead or E6, whichever you like to call it. And then I quit Facebook 6 months ago to start a machine learning platform for life science and in particular, de novo protein design. So that's what I do. I'm going to talk about, we know that machine learning changes all the time, and everything that we know that was edge of the science becomes old very, very soon. This is a very, very fast moving field. And we're going to talk about all the changes that happened, particularly in the last 2-3 years. So we get on top of everything. So we're going to cover the last 3 years, and mostly in the lens of ML practitioners, industry people, startup people. We're not going to be focusing on much on the science and research side of the things. So we're going to talk about things that have become more mainstream and industry standards for the last 3 years. We're going to talk about transformers, few-shot learning, and everything in between, like how do we move from label data to more generic type of data set, how we move to unsupervised learning and semi-supervised learning and deep reinforcement learning. We're going to talk about all these techniques and accomplishment and things that have changed in the last 3 years. So we have good toolbox going to next 3 years. So we build better startups, we have better jobs and everything. So first, before we get to what happened in the last 3 years and what we think the future is going to be, what do we mean by ML 3.0? This is kind of how I see the evolution of machine learning in last 20 years, let's say. The first era for me is machine learning 1.0, which we have tiny models and we have very like small statistical models like linear regression or logistic regression or random forest. Small structured data, small models, obviously smart hardware at the beginning of everything. And things are not productionized. We don't talk much about the usage of ML industry at the time, right? This is pre-deep learning era. And then the second phase, machine learning 2.0, I call the deep learning era. So deep learning era, which is basically, we talk about CNN, RNL, LSTM, all the techniques. It's mostly about the techniques and it's mostly about the deep learning architecture. We see bigger models, we see more data, mostly labeled data, and we see the architecture is getting more and more complicated, deeper and deeper neural networks. But in this era, we mostly talk about one data set, one task and one model. The model gets very complicated, but at the end, it's just one model mostly. And one training, right? There's just one thread of training. So, and obviously the biggest accomplishment of this era, you can talk about ImageNet, and at the end of it, AlphaGo, which was more reinforcement learning, but this era is dominated by deep learning and in particular ImageNet. After 2000, I think things start changing, and this is the topic of this seminar. Mostly, if I want to say like one thing that differentiates this era from the deep learning era is the fact that this is mostly about connecting the models together, connecting like all these large models, all these large into one giant architecture that help us serving one industry task rather than focusing on one particular problem. I'll get into the details of that. So all the changes that happen, I break it down to 4 different dimensions. I dimensionalize all the changes in the last 3 years to 4 basically topic. Data, so how our mindset and how we think about data has changed. How we think about what are the techniques, what are the new techniques that came up, and more importantly, how do we combine these techniques to build larger systems? These are the first three topics. And then the last topic is how do we go to the real world? How do we productionize these models and deliver value to the real world, and how do we automate this, and all the things that are the externalities of the machine learning, and they're not necessarily machine learning. So we're going to talk about that. So basically, the first one is data. We can see in terms of data, the biggest change that's happening, and actually has happened in the last 3 years, when you design a large system, instead of one data set, you have to deal with many data sets. Many data sets that have different sizes, different shapes, different modalities, and they're not necessarily labeled. There are a lot of self-supervised learning and semi-self-supervised learning, and there are new type of data sets that are coming to this new world. For example, graphs is one big new thing, and then genetics data. We're going to talk about all of them. The second dimension that I want to talk about is how we connect all these models. And I think this is the biggest differentiation of ML 3.0 to ML 2.0. We don't talk about models as much anymore. We talk about how do we combine them, how we put them on top of each other, how do we put next to each other in different types of configuration, so we deliver one giant task instead of one particular task. One giant task that is basically has many tasks inside. So as far as the system, instead of one model, we have many models that talk to each other and communicate to each other with different sizes, and they have various owners. Each model could be designed or even trained by different teams. And at the end, as a machine learning engineer or as a system designer, you have to put all of them together to deliver the industry task that your job is. And then there are a lot of new issues has come. Once we go to industry, there are a lot of new issues comes as far as privacy, bandwidth, regulation, everything else that I'm going to talk about. This all goes under system. And then the last two dimensions are the techniques. Obviously, that there are three techniques: transformers, GANs, and deep RL, that to me were the bigger techniques that came up in last few, became more mainstream and became more industry standard. And then at the end, I'm going to talk about how things become more industrial scale, how things become more got into real life. So how applications went from just some models in some developer Jupyter notebook to the real life, and they're being productionized. And then obviously the compute infra, these are becoming more and more important, and then automation becomes important as you go to real life. So I'm going to talk about all of them as the fourth dimension of the changes. So the first dimension, as I said, is all about data, right? So a few changes happen. I'm going to get to the details of each of them. The first change, we moved more towards supervised and unsupervised. If you think about it, like, this was very inevitable, because when we talk about supervised is very hard. You have to spend a lot of money and a lot of time to find this large labeled data sets. But internet and the world is full of many unlabeled data sets. You can automatically generate your own labels. That's how everything is going to. So basically, we're going to, so everything is becoming unsupervised or self-supervised or semi-self-supervised. Like, you can think about everything, mass language models, basically vision is going through that, everything. Like, if you're training a social media like recommendation engine or ads ranking, so everything is basically semi-self-supervised. You're learning clicks and CTR, which are all automatic generated from the data. So everything is becoming self-supervised or semi-self-supervised. The second thing about data that is changing, everything is becoming multimodal. It used to be you work with one type of data set. This is changing. So if think about a human brain, so the way human brain works, we can never say, okay, at this moment, I just want to focus on one type of data. When you walk on the street, there are many types of data, the voice, and then the images, and everything. You're consuming all sort of data, and you're analyzing them all the time. This is going the same thing happening to a machine learning system. You have to analyze everything. in particular, like if, for example, in ads ranking, right? You have to be able, like if your ads recommendation, or let's say for YouTube recommendation, right? If your YouTube recommendation wants to work well, it has to be able to understand the text, basically the comments, the content of video, that would be video or image understanding, and then all the tabular behavioral data. So there are many different modalities of the data, and if you want to build a system that actually works, it has to be able to read through all of them. And the simplest way would be to just have submodels, just simple neural networks or whatever architecture that you want to borrow to understand that particular modality, and then have an overarch that combines all of them together and train it end to end. That's basically the simplest architecture. The third thing about data that has changed, we moved we started to get a lot of graphs data, right? Social media and internet and ads and recommendation engines taking over the entire ML industry, graphs is becoming more and more important. So basically, if you want to recommend a friend in social media, this is a graph question, right? So if anything about node classification or predicting edges, anything about friend recommendation, anything about any recommendation in social media, and every time you connect humans or any nodes together in machine learning, that falls under umbrella of graphs and graph neural networks. That's another big thing that has been growing in the last few years. So this is as far as data. The second piece of the changes, the second dimension of the changes, is the most important change that I see in the last few years, and that's about borrowing large models trained on large data sets, and then combining all of them together to train some downstream task to deliver something that is your desirable, like, industry question, right? So there are many different architectures. There are many different configurations or systems that you can design that put models together. The most common one, and I think if you don't do this in 2021, your system does not fully utilize the modern machine learning, is transfer learning. So transfer learning is exactly, again, the way human brain works. We understand some context, some generic context, and then based on that, we learn some downstream tasks. And that's how we get to learn new things and more specific and more abstract tasks all the time. So, for example, if you want to learn driving, you bring all your knowledge from physics and all your knowledge from common sense to driving. Nobody needs to teach you that if you drive a car to cliffs, that's a bad outcome. You just borrow that from physics and you bring it to the driving board. So all the time, you take some context and you use your learning to train some downstream tasks. That's how our brain works. This is how machine learning is moving toward too. So one example that was a project that we did 3 years ago was a fashion classifier, right? So this was a project that we used a lot of semi-self-supervised and transfer learning. We could use the tags, the text tags next to every image on the internet, so we can classify some auxiliary task. And then once using some like pre-trained large ImageNet algorithm, and once you have those embeddings, you can classify your downstream, which could be a fashion classifier, or it could be a style picker or anything. And that is basically how you can utilize some already pre-trained joint network to do your industry task. So there are two very similar ways you can configure this. There's transfer learning and there's multitask learning. Transfer learning is mostly, you can think of it as a sequential learning. When you learn something, and then you move to some downstream task. They're sequential. You move the knowledge, which is your the weights of your network or your embeddings, your representation, whatever. In multitask learning, everything is in parallel. Then you have few objectives and you can train them at the same time. That's called multitask learning. So this is the first configuration. The second thing, sorry, let me get. The second thing that is becoming very popular is few-shot learning. What is few-shot learning? Few-shot learning is when you have very, very limited number of data and you want to learn something. And this is very common. For example, you can think of it as a medical data or cancer data, right? You don't have millions of data samples like genetic sequencing or imaging or whatever data that you want. You don't have millions of those data. So the only way is to have some large auxiliary tasks, you train over them, and then you just bring the knowledge to this downstream task that you have very, very limited number of data from. This is called few-shot learning, and it's basically extreme case of transfer learning. You can think about it, that your model learns a lot of generalization over one or many auxiliary tasks, and then bring the result to one particular task you don't have enough labeled data for. Or like one example would be that, for example, understanding the name of the birds, right? If you already have many tasks that could be, for example, localization, or basically the tasks that understand the concept of the birds, that could just do the object detection. If you have many of these type of tasks, or you have more downstream tasks that can understand the name of the animals, you probably need a few samples of pictures of the birds with their names so you can do the classifier. So this is basically few-shot learning, which I've never done a project with, but this is growing very fast. The third kind of configuration that I can see that is growing a lot is federated learning. What is federated learning? Federated learning addresses this particular problem, that a lot of time, and this is becoming really big, a lot of time for privacy or for performance purposes, you don't want to share data, right? Your data is collected in some nodes, but the nodes do not want to share the data to the main server for many reasons. For example, one would be hospitals data. Let's say you have hundreds of hospitals in your system, but for privacy reasons, they do not want to share the patient's data with your service, right? Or for performance purposes, in terms of IoT, you have a lot of devices, but you don't want them to send you pictures, and for bandwidth purposes, basically, you do not want them to send you everything all the time. So in that case, you start training on the edges, you start training on these devices, and then you just send the summation or whatever the conclusion of these weights or models, you just send the results to the server, which is much lighter than all of the images, and it's privacy preserving, right? This is becoming a very big thing. If you followed all the Apple iOS 14, the signal loss, the reason Facebook, Snap, and Pinterest lost a lot of money, probably north of 100 billions, that was because Apple basically banned them from collecting third-party signals. And the biggest solution that is introduced for that is privacy preserving ML, which is mostly federated learning at this point. So this is becoming pretty big for advertising and for a lot of other industries. So that's the third type of approach that I see people mix up different models. So this is very different. Transfer learning was very different. This is basically the same models that just run on different edges, and then you combine the result on that. There are many other ways that you can combine models together, and they're becoming more and more increasingly fashionable in machine learning engineering. For example, mixture of experts, or having submodels, which is one of my favorites. So you want to run you want to have different experts that look at some part of your data or look at your entire data from one perspective and then combine the results. That's one of my favorite things. So this is, I think, the biggest change that I see in machine learning 3.0 and the biggest change that the machine learning world is going through. It's not about one model, one task, and one training and one data set anymore. It's about many data sets, many tasks, and many models. And your job is not to, I mean, your job is still to come up with the best model, but it's not necessarily to build those models yourself. You can borrow them and just assemble them and just build this giant system that is basically plug and playing all these models together. That's becoming the #1 job of machine learning engineer that I can see. Just using transfer learning, use few-shot learning, use federated learning to assemble these things together. That's why a service like Hugging Face or a company like Hugging Face is becoming increasingly important in this industry, because it just gives you all these models, the code, the standardization, and then the service, so you can just borrow things, plug and play them together, and build this giant service. That's the game in my mind. So that's as far as the biggest things that I see in machine learning 3.0. Now I get to the techniques that became more and more popular in last few years. The biggest thing was deep reinforcement learning. Everybody could say, oh, this is not even new, this has been around forever. But in terms of industry and in terms of actually delivering these results, this is, again, something very new, and it's not even very mainstream in industry still. So basically, reinforcement learning, the way I look at it, is the machine learning that comes to life, and it can it can talk to the environment, collect the rewards, understand the states, and then update the states and then the rewards, and plan for some long-term objectives, right? That's how I look at reinforcement learning. Let me move myself so you can see. This is pretty much so you have an agent, the agent does an action in the environment, and then the state of the agent changes, and then it gets some reward, and it keeps doing this. So this is basically more than being a technique. I look at reinforcement learning as a framework, as a problem more than a solution. So reinforcement learning is just a problem definition or a framework that has been around for many years. What has changed is now you can model your policy, you can model your environment, you can model your values through deep learning, and that has become very powerful. That made reinforcement learning so powerful. So obviously it needs massive data. It needs way more data that we have in deep learning. It's worked pretty good for games. And obviously the biggest result that we had was AlphaGo 2016, if I'm not mistaken, then AlphaGo 0. Then the FAIR used it for, so this was from DeepMind, Google, and then FAIR used it for beating some Texas Hold'em champions. So it's becoming bigger and bigger. I heard YouTube is using it in their recommendation engines. It's becoming bigger and bigger, but still it's not very mainstream in the industry. So this is one of the biggest techniques that is growing. The next one, that is, if I have to say one technique that dominated the machine learning industry in the last few years, is definitely transformers. Transformers started from the 2000s. If you want to give it a date, you can probably date it to 2017. The paper Attention is All You Need. That's where transformer got really big and it became more mainstream. It's the main usage is for NLP, text summarization, sequencing data, and it's an attention-based architecture. I don't want to get much into details of it. Let me just not get to any details. The main advantage of transformers over the older sequence analysis or NLP models as RNN or LSTM or all the other ones, those were all sequential. This is very parallelizable, and so it's a good match for the world that everything goes through GPU and everything is parallel. It's a very powerful technique. It started for sequence and NLP and everything, and now people use it for everything, for audio, for video, and now for images, for everything. It's becoming very, very standard. And if somebody wants to study transformers, the best resource that I learned the best from was Introduction to Machine Learning from Duke University. That was the best course about transformers. It's not only transformers, but the transformer part of that course was my favorite. So that's about that. The next technique or topic or architecture, whatever you want to call it, well, that got very popular in the last few years was GANs, generative adversarial networks. So this concept introduced 2014 by Goodfellow, and then it's an architecture that you have basically two neural network, two like actor and critic neural network that they talk to each other, and over many rounds, the critic starts understanding this first, and the actor starts like generating things that become more and more like the real distribution that you provided to. So this is becoming a thing. So if you look at that account, cuckoo.ai, which is an Instagram account, it's a project that I did in 2018. So these are the three of the paintings that it was a project that I did 2018 that I wanted to generate a bunch of abstract paintings. I used various data sets, some abstract paintings, some real images, and I combined them together to generate this. If you want to see the outcome, you can go to this Instagram account, cuckoo.ai. These are from 2018. So back then, this was kind of hard to do. I think today it should be pretty easy to deliver such results. So their GANs are still pretty unstable, and I've seen people use it for different tasks. Even recently, I saw people use it for protein designs, for drug discovery, but they're pretty new. They're not mainstream in any way. People use it for data augmentation, something that I don't like much for many reasons that I don't want to get into now, but it's finding its own applications. So this was the third techniques. Now I got to the last part of the presentations, that externalities of machine learning, right? So we have the data, we have the techniques, and we have the systems that how you combine them. These are the three changes that we went through. But now I want to go to externalities and then the miscellaneous. So the first thing that is becoming more and more important is MLOps. So what do we mean by MLOps? MLOps is basically, to me, the last mile of machine learning, and it's more of an engineering than a machine learning science. So what do we mean by that is now that you have your models, you have combination of your models, and you train it and you test it, and whatever this model needs to get out of your laptop and or whatever cloud that you use and go to real life, right? It has to deliver some outcome. So everything, deployment, maintenance, you want to deploy and maintenance so it works reliably and efficiently, right, in real life. So this could be a YouTube recommendation engine that you design, or Facebook ads ranking, or some self-driving. This has to be reliable and it has to work. Otherwise, you don't want just the car to like 1% of the time it fails and just run into some other cars because you didn't deploy this correctly, right? So these are all MLOps. So transition the algorithm to production. That's what MLOps is. Well, deployment, automation, reproducibility, and predictions obviously is a big piece of it. Diagnostics. You need to have a service that just diagnose the entire engineering pipelines to make sure everything works correctly. And then now that these systems is becoming bigger and they're part of everyday life, they have to go through the governance, regulatory compliance, all these complications that are not necessarily engineering and machine learning jobs. And then scalability. Obviously, if you're letting this large system to the world, you have to make sure that they scale, right? Because, for example, if this is a YouTube recommendation engine, you have to make sure that this is scalable. If you have if the number of queries per second just for some reason went 10x, this system is reliable and is scalable. So all these things are becoming part of MLOps. Monitoring and management, obviously, a big part of it. So MLOps is becoming bigger and bigger. There are a lot of companies who take care of this. If you're interested, this is a great topic to become expert at. The next topic is AutoML. So as machine learning becoming bigger and bigger, like everything else, we want to automate it in different levels. For example, the simplest thing would be for data preparation. And the simplest thing would be that, okay, let's automate the column type detection. So you know this column is a string, or it's a float or integer, so you can behave accordingly, right? Your models can just pick on that, or it's a categorical data or whatever it is. So that's one simple thing. Feature engineering is a big part of automation. Feature selection, transfer learning, missing values obviously is a big part of automation. Model selection is a big thing, but it's more of a dream at this point rather than real. I don't think if we think in like general model selection, I don't think there's some real system that does that. Hyperparameter optimization is a huge thing. Just if you work in any of these companies, they have a lot of models and you need to automate this hyperparameter optimization. Otherwise, this takes forever. This takes the life of all your engineers and data scientists to find the right hyperparameterization. And it's a very heavy job. This is a very compute heavy job. So that's as far as AutoML. The next thing that you need to know about, at least some, is hardware acceleration. So as these models get bigger and bigger, they're becoming more and more compute hungry. So we're moving toward GPU and TPU, and GPU and TPUs are the teraflops, all their numbers are increasing. By the Moore's law, you can just look the specs up. Basically, the compute is growing, the memory is growing, everything is growing exponentially. So the things that you probably need to know as a machine learning engineer is, one is the software libraries that sits on top of these hardwares, for example, CUDA or everything else. So you can connect to and then utilize them well. This is one thing that you need to know. And then the second thing that is becoming very, very big, especially for more senior people in these companies, is understanding the economy of these devices. So usually you have a choice that what type of GPUs or what type of TPUs do you want to purchase or you want to use on cloud. And this is very important. The cost of the device, the energy consumption. For example, if you for machine learning applications, you usually need larger memories than, let's say, web applications. These are all concerns that you need to understand, and you need to be able to manage these answer these economical questions about hardware, because you don't need to be the designer, you don't need to understand the details inside, but you need to be able to do some analysis to understand what fleet of hardware is the right fit for your machine learning strategy. So this is becoming bigger and bigger. So we're getting to the end of this presentation. So 33 minutes, this is not bad. So I'm going to talk about the breakthroughs very fast. The two main things in last 3 years for me was, first, obviously, GPT-3 that everybody knows about and everybody talked about. It's a transformer-based architecture by OpenAI, 175 million parameters. This was a massive model. And basically, this is something that everybody talked about. I don't want to talk more about it. OpenAI keeps working on this. If I'm not mistaken, they had a $1 billion licensing agreement with Microsoft. So this was basically made OpenAI profitable. I don't know if they invested that money or they gave it to them, but this showed like how valuable this could be. And then the second thing that is my absolute favorite, and that's how basically, that's not exactly why I quit Facebook, but that was one of the biggest things that persuaded me that this is becoming very big, is AlphaFold 2. AlphaFold 2 was a project by DeepMind, Google, transformer-based again, that is basically there is this central problem in biology. So if you look at these pictures on the right, these are the pictures of two proteins. There's this very central problem in biology and medicine and drug discovery, that predicting the shape of proteins. These proteins are just some sequences that fold into 3D dimension and take a shape. And based on their shape, they deliver some functionalities in your bodies. And if they're misshaped, that could cause cancer or anything. Anything from like COVID to cancer to Alzheimer's could pretty much be explained by the shape and the volume and the functionalities of this protein. So it was very, very central and was very, very big problem to predict the 3D shape of these sequences. It used to take up to 2 years, and you had to, it was very expensive to find the shape of these creatures. So the computational models before AlphaFold, they had accuracy up to 40%, which is obviously pretty low. The DeepMind team got to something around 60% the first year that they started competing with all the other teams, and they got to 87% accuracy, that you can see here how close these shapes are together. So that's basically solved one of the biggest open problems in biology or biochemistry, whatever you want to call it. And this was the biggest breakthrough for me. This is something that I expect to hear more and more from. That's basically my day-to-day job for last 6 months. Also, there are a lot of others. So 3D prediction of 3D shape prediction of protein is one problem. There are many, many problems about proteins that I think they're becoming more and more important for next 10 years. I think this is becoming the most important usage of machine learning for the next decade. So that's as far as the breakthroughs. We're getting to the end of this. I want to end it with basically what could be the next topic. So if you look at the machine learning, if you look at the industry, still the #1 usage of machine learning, the largest machine learning teams in the world are focused on some sort of recommendation engine, whether it's in YouTube or Spotify or Instagram for content recommendation, or in Amazon for whatever purchase recommendation, e-commerce recommendation, or in Facebook and Google for ads recommendation, as you call it, ads ranking. So it's some sort of recommendation. Still, that's the largest machine learning industry usage. So obviously, FAANG companies are the largest users of machine learning. NVIDIA is becoming more and more increasingly the infrastructure of machine learning, and they're very good at even explaining to the world how these models could be used. And these are the older companies that they're not necessarily ML or AI companies, but they're heavily into this. But we're getting increasingly more startups and new companies that are just machine learning first companies, like Scale.ai, like OpenAI, like Insitro, or Hugging Face. So self-driving is becoming a big thing. Obviously, Tesla is leading in a Tesla and Waymo. This is becoming a very big application. OpenAI, everybody has heard of. Scale.ai, the company that is mainly focused on machine learning tools, vision, self-driving, and everything around that. Insitro is a company that started by Daphne Koller. This company is in drug discovery, basically understanding proteins, small molecules, collecting massive data sets, building these large models to speed up the process of drug discovery and everything. These are becoming machine learning first companies. We didn't have companies that they're just machine learning, and they're getting larger and larger. Scale.ai became a $7 billion company last year. Insitro raised more than $700 million. OpenAI has raised as much as everybody knows. Hugging Face is becoming pretty standard. It's becoming pretty big. Every machine learning engineer I talk to use it on a daily basis. And there are many, many. I can say like maybe there are thousands of these companies, obviously smaller than these ones, that are just machine learning companies. And the industry is getting bigger. So this could be, if you want me to do more of these videos, I can do one about the industries. Another one would be to cover the startups, only the machine learning startups, the newer ones. That would be another topic. ML 4.0, what do we think machine learning is going to go after this era? That's also another topic I'm interested. Web 3.0, which has nothing to do with machine learning, it's just metaverse, everything. I mean, it does have a bunch of things machine learning, but that's not a machine learning topic. And then chips industry, that's again adjacent topic, but not necessarily machine learning topic. And then usage of applications of machine learning into life science. That's something that I'm very into. If you're interested, we can do another video about that. Anyway, that's it. Thank you for listening. And this is the end of my presentation about ML 3.0. I'm going to open it up for questions. So I'm going to let you ask the questions as text. So it would be very hard.